Hello, and welcome to A Snapshot in History. I'm your host, Matthew.
I'm your co-host, Akhil.
And today on our show, boy am I excited for this, we have a very special guest. A man with very stylish hair, but more known for his works. Ladies and gentlemen, please welcome Guillaume Francois Antoine, Marquis de l'Hôpital, Marquis de Saint-Mesme, Comte de Entremont, and Seigneur de Auquest la Chaise. I hope I didn't butcher that.
Oh, yeah, you definitely did that.
It was close enough. Thank you very much.
So, L'Hôpital, this is your first time on the show. We'd like to learn a little bit more about how you got into math and just what you did as a child. Would you like to explain that to us?
Sure, I'd like to talk about my roots. I was born in Paris, France in 1661. As a child, I struggled in almost every subject except math. Math was where I found peace, and it was something I excelled at. I later joined the French military. After I retired from the military, I started cracking down on mathematics and started making proofs. It was in 1696 when I started to develop the proof I'm most famous for. I'm sure we'll talk about it later, so I won't give too much away right now. But that had to be by far the greatest accomplishment of my life. As a side note, I married my beautiful wife, Marie Charlotte de Romilly de la Chesnellet, and have 4 amazing children. 1 son and 3 daughters.
Wow, that's a lot of information there, but I thank you for that. I feel like I really got a better understanding of where you came from.
So now, I'm sure most of you mathematicians right now are wondering, and all you guys want to know, you've been through all your math classes and you've dealt with L'Hôpital's rule, but now it's time for us to jump into the next segment where L'Hôpital explains his extraordinary proof.
I don't know about you, Matthew, but I've been waiting for this ever since we started this show.
And we're back. Sorry for the long wait, guys, but it's finally time to get into this proof. Later into this segment, we'll be contacting an admirer of yours, L'Hôpital, and an expert in your theorem to help us explain it.
Alright, great. I made a PowerPoint telling me to explain my theorem.
Oh, cool. So we'll put the visual to go along with your explanation right now.
Alright, so where do I start? My rule states that if you're given the functions f of x and g of x that both have a value a such that f of a minus g of a is equal to 0 and are differentiable near a, the limit x approaches to a of f of x over g of x is equal to the limit of x approaches to a of f prime of x over g prime of x. And this only works if g prime of x does not equal to 0. And my proof also uses the mean value theorem, and here's a recap. We have 2 functions f of x and g of x. Let's set a new function h of x equals f of x minus f of b minus f of a over g of b minus g of a times g of x. Let's first set x equal to a, and h of a equals this as shown on the board. Combine the fractions by multiplying the left side in purple by what's shown right there, and distribute the right part to get h of a equals this. The parts in red subtract out, and we are left with h of a equals this. If we do the same but instead set x equal to b, we get h of b equals this. Where again the part in red subtract out and we are left with h of b equals this was shown on the board, which is the same result as setting x equal to a, so h of b equals h of a. H of a equals h of b, so therefore h of a minus h of b equals 0, and by Rolle's theorem there exists a value r on the interval a comma b such that h prime of r equals 0. We add the gray part over to the other side and then divide g prime of r, and we get this, was shown on the board. Now for actually taking the limit, as shown on the board. We know from the preconditions of my rule that f of a equals g of a equals 0, so we're left with this. Take the limit of both sides, as shown on the board. And since r is always a value between b and a, the limit of b approaching a is also equal to the limit of r approaching a. So therefore, what's shown on the board is what is in the end result.
I have one question for you, L'Hôpital. I've studied this proof intensively over the course of my career, and I've been baffled about how you managed to use Rolle's theorem only soon after it was embedded in your proof. Can you explain that?
Great question. He once suggested that there were difficulties associated with the axiom given by myself. I took that into consideration when finalizing my proof, and boom, my proof was complete.
Wow. I'm beyond impressed what you have done to revolutionize the math world. Thank you very much for that insight.
Great. That was a very in-depth segment right there, and we're going to start to transition to our next segment, where we'll be discussing the use of the rule in basically our everyday lives and in your high school classes to everyone that's listening. So thank you.
And welcome back, guys. It's great to see you again. This is our third segment, and here we'll be discussing the uses of L'Hopital's famous rule.
All right. It's such a simple and looks easy to use, but in fact, as I said earlier, there must be a certain conditions met. If those conditions are met, we can use those rules in a variety of situations.
Like what?
Like here, I'll give you 2 examples.
For this example here, we have to find the limit of x squared over 2x as the limit of x goes to infinity. So by using L'Hopital's rule in this equation, we can rewrite the equation of the derivative of the top and the bottom. Since, say, we plug in infinity, plugging in quotations, of course, you get infinity over infinity, so we can use L'Hopital's by there. As we take the derivative of the top and bottom, as you can see here, follow along, we eventually get to the end here, after taking the derivative of the top and the derivative of the bottom, doing a little algebra here and there, and then at the end we eventually get 0.
But that was pretty easy. That was light work, if you ask me. How about you give us something harder?
I bet. Try this, boy.
So this question asks us to calculate the limit of t as t goes to infinity of t cubed root t. So first we will let y equal to t cubed root t. And after taking the logarithm of both sides, we will get ln of y equals ln of t cubed root t, which will simple out to 3 ln t over t. Now, by taking the limit of as t goes to infinity of ln of y equaling 3 ln of t over t, and taking that limit as t goes to infinity as well, we would get infinity over infinity. Therefore, by L'Hopital's rule, we will take the derivative of each respective one individually, separate. And by doing so, we will get that the limit of as t goes to infinity will equal 0. Therefore, the limit of y as t goes to infinity will equal e to the 0, which will equal 1.
That was a lot harder, I think so. Do you think?
I think that was a lot harder too.
I think we got it, though.
Yeah, we did. And I think that should help a lot of our BC Calc students out there who are listening in right now. So in our final segment, we will wrap up our time here with L'Hopital, and we'll discuss some of the real-life scenarios using L'Hopital's rule, as you can see pretty much anywhere around the world. So we'll see you back again for our last segment.
So, welcome to the final segment, and as we transition into here, we're all wondering the same thing. Where did you get your hair from?
No, we're just kidding. If possible, could we see your rule anywhere outside the classroom?
Yeah, of course. My rule comes in handy by proving the continuous compound interest rates in investments, different types of bank accounts, or when paying credit card bills, mortgages, and etc.
I never saw it like that. I'm gonna try that when I get home.
Well, that's I'll try that too. So that basically wraps up our segment today of Snapshot of History. We'd like to thank you so much, L'Hopital, for being here today and joining us. So round of applause for him.
It was my pleasure for having me. Thank you.
And thank you, listeners, for tuning in today. And we hope that you can join us for the next segment and our next podcast on Snapshot of History.
Signing off, this has been Akhil.
And your host, Matthew.
Have a great day, everyone.